Okay, hello. Welcome to NET403. My name is Stephen Callahan. This is my colleague, Georgie Vasquez. And we are both engineers on the Amazon Infrastructure Organization. This is our talk about how everything from robotic cats to tiny plastic connectors make the infrastructure work at planet scale. As a bit of an agenda, we'll talk about what we think the role of the AWS network is. And then we'll get into some of the interesting challenges that we've seen that lead to these design stories of the internal products that we build and the goals and principles that come out of it as to how we will build future things up and down the stack. And this is all rooted in the deep ownership that we have and how we're able to make changes at multiple different points along the infrastructure. And then towards the end, we'll talk a little bit about how we see applying these goals and principles against the future challenges we see coming up. This is the third in a series of talks that we've delivered here. It's still new for us at the infrastructure organization because we're not here to talk about an AWS service or a new platform that you can use. But what we're here to do is to give you an understanding of the lasting impression and the mental models that should give you the experience you expect from the AWS network. So feedback from last year's talk was that you wanted to hear a bit more about the backbone, how regions connected together, the controller ecosystem on top of that, and some more of those physical pieces that I mentioned. I've also brought props with me this year, so we'll use them a little later. It's also useful to know and understand the relationship that infrastructure networking has with the other networking services at AWS. And so there are service teams here to talk about NAT Gateway and CloudFront and Route 53, but we're here to talk about the infrastructure pieces. So the data centers, the routers, the switches, the fiber cables, that's the land that we work in. So when we went about trying to figure out what we wanted to talk about this here, we saw there was lots of interesting and innovative things that were happening across the globe. But the longer we spent at it, the more clear there were some underlying themes that were important to get through. And these are the things that we use to tackle all of the challenges of building across the globe. And when we did it, I think, in my opinion, it all boils down to one thing, and that is the ownership that we have. Yes, it is an Amazon leadership principle, and yes, we want to do things like work backwards from customer requirements. We want to make decisions quickly, but I believe we can be most successful in our role by going deep into that ownership area. And so in previous talks, we've talked about the custom network hardware that we have, these custom boards that serve us in specific areas, the transceivers and how we manage the network, the custom control planes that we've built. However, all of these things are still quite tangibly close to the routers. And I think we go further up and down the stack more than you might expect. So to set a baseline of what we think the role of the AWS network is we want to be so performant and reliable that we're out of the way of your workloads. We do this every year with increasing scale. And with that increasing scale and stronger requirements, the only way we can see to do that is to go deeper into ownership. So with that in mind, let's look at some of the design goals and how we think about achieving that role. The first thing that I always put up is we aim to be flexible. It's not useful for me to build single-purpose networks, one for database, another for storage, a web server, even InfiniBand. Their ability to cater for emerging workloads is limited. And we think to meet the future needs that you will have, we don't want to be limited. We think that's going to give you a poor experience. So to give you an example of this, last year we were here and we talked about UltraClusters 2. And these are the networks that underpin the machine learning and AI workloads of our customers. And yes, if you've got AI on a buzzword bingo card, you can tick it off for this talk. As we've gone working around these areas, I've been astonished at the use cases that have come up. And this is because ML workloads are far more varied than we thought. If we start with the headline workloads of LLM training, there are some customers that we have that want to connect dozens of buildings of accelerators together and use it as a giant pool of capacity. Other customers want things a little bit more segmented. And so what we've done is we're able to connect these buildings anywhere from a handful of terabits per second of capacity all the way up to multiple petabits of capacity between any two buildings. If we then look at the other side of the coin, on the inference workloads that we see, these are extremely latency sensitive. Some models exist purely on a single node, but we're already at multi-node models for some of the larger frontier models. Sorry, multi-node inference for some of the larger models. We even have distributed, where these models are across multiple racks, multiple data centers even. And what we don't want to do is optimize for the wrong set of workloads. Even on our general purpose network, we deeply care about low latency. And so I've been fortunate enough to previously work on the Outpost and local zone products. And talking with those customers, there's always a trade-off. We can talk about larger pools of capacity back in a region, or have latency-sensitive applications down towards the edge, something like online gaming. But all of these decisions and trade-offs have effects, both on cost, redundancy, and performance. To kind of complete this journey, we also can look at video streaming. And so this is high bandwidth, high quality requirements. And we've previously posted a really good article about the behind the scenes of what makes Thursday Night Football work. And this talks about dynamic ad insertion and the requirements of a production versus distribution. We even add predictions into things like Formula One that enhance the end user's experience. And so all of these are time-sensitive workloads that we want to take into account when we build these products up and down the stack. So I've mentioned it a few times. What is the stack? Well, I'm a network engineer, and so I'm rooted in the OSI model, and I live at layer 3. And what I think of is, by having extreme ownership, I'm free to move up to layer 7 and talk with customers and talk with internal teams like Bedrock and Lambda on what future things are coming up. What way do you see the requirements changing in the near future? I can also then visit the lower levels. I can visit layer 1, and I can talk with our network platform development team and our fiber infrastructure team on new technologies that will also affect the layer 3. All of this kind of leads into the design goals. So we take all of this input, and we have a set of goals that we work through as we're designing these products. So here's a subset. These are just 3 that I chose because this is how we go to approach new challenges. And this may be a new internal product that we need to bring, or it may be enhancing an existing product that we already have, like the Ultra Clusters 2. And this happens every planning cycle. And this just happens to be now December. We are completing our planning cycle for 2025. So here's a couple of examples. Firstly, our top priority is security. And I don't say that just to pay lip service, but what we do is we think of when we anchor something at the top, it's interesting as to what things flow at the bottom of those decisions. And so physical security is a given. We want encryption on network links that leave my control. We also work with the VPC team for their encryption, which sits on top of it. But it's also down to physical security. Like, I, as a network engineer, am not going to visit a data center to fix a problem. That means the network needs to be designed to be operated by the people on the ground. So I need to make sure we're providing the right tools for the data techs to do their job and prevent mistakes from causing an issue. This is also evident in the role of the internet security at large. So a few weeks ago, working with the Department of Justice, we were able to produce evidence to stop the anonymous Sudan cybercriminal DDoS as a service group. This hopefully makes the whole planet a little bit safer, and it's also a rare day when it's good for AWS to be in the mainstream news. The next design goal that we have is availability. It's because the infrastructure network underpins all AWS services. If we're having a bad day, everyone's having a bad day. And we also have this availability bar growing. As our scale increases, we can't keep the same proportion of events that are happening with increased scale. When I look at availability, I also think of consistency. It's no useful for me to hold on to your packet, your message, for 2 seconds. By the time you get it, it's stale, it's no longer useful. And so the network engineers among you in the room may recognize this as a smoke ping graph. And this is from an instance I spun up in US West, and it's showing a fairly reasonable 700 microsecond connection to an instance, to another instance that someone else is maintaining. And I can also see some smoke there that kind of goes up to about the 1 millisecond. But overall, I'm looking at this going, this is a nice consistency graph. This is a target of what I want the network to look like. The next thing in availability is resiliency. At our scale, we can't avoid failure. We must plan for it. This also means we need to understand the effect of failure at different points of the network. And so what we like is we want to choose where we're going to handle the failure and choose whether we are going to react quickly or we want to react just once and avoid unnecessary churn. So let me give you an example. If I set up a standard region with 3 AZs, and let's go beyond the logical and add some physical elements to it. So I've added some routers, an optical mux, an amplifier, and the fiber path. Now, if I add an application on top that's doing something like a heartbeat message between these 3 AZs, if we were to take a fiber break in the center, that would cause the traffic to have to reroute from A to B back through C. Now, this works, it's great. We have resiliency, we are continuing the traffic. But fiber cuts can happen randomly. We don't control when that happens. And I don't like this big of a change to happen when it's not in my control. So what we did is we looked at adding a second fiber path. And so we have resilient fiber paths that don't share the same conduits. And if we have a fiber cut on path X, the system, using a technology called optical line protection, can switch over to a secondary fiber path in low-digit milliseconds. So this is a nice fast response that to the application looks like nothing has happened. Now, it wouldn't be a talk of mine if we didn't have some gory picture fun. So on the left, we have one of these things I would classify as a necessary evil, would like to uninvent, but it is aerial fiber. It exists in some regions, but unfortunately, trees can fall on it and buses can crash into lampposts, which has happened. And what you see is a fiber cut there, and that there needs to be repaired. On the right-hand side, you have what I would classify as some over-eager construction workers who used a backhoe to dig up our fiber. Now, the advantage with the one on the right was we had our fiber sensing technology, meaning when this impact happened, we lost a grand total of 13 packets. Now, I'm sad for those packets that ended up on the floor, but I will take 13 packets over a multi-terabit link being severed like that. But building this resiliency into my optical line protection does not give me a free pass. We still want to be able to take the entire path out of service. For example, if I want to do an amplifier replacement. The advantage in this case is the traffic will still route down toward the availability zone C that we had before, but this is going to happen less frequent. It's going to have a shorter duration, probably because there's someone in the data center doing it on a planned notice, and we'll have spares in the warehouse. Additionally, this is not going to be dug up by a backhoe or have a tree fall on it. So this is a controlled way, and we have the resiliency that we want. Now, what you will note from this is if I'm going through availability zone C, that's going to increase the demand on that system. And so we need to have a capacity management system. So as with the theme of the beginning, this is owned, created, operated purely by us, and this is the capacity management system we use for planning all of our infrastructure. And so the role of this system is for predicting where the traffic will go, understand what trends exists, and what demands that we have. We also embed in this how resilient we want the network to be and what consistency targets that we have. So this is a pretty complex dance because we're going to add a new site to a region fairly regularly. We're going to scale existing spans or add new spans. These are all options the system can bring. Plus, we also want to do this months in advance. We can't plan and it has to be done tomorrow. We want to give enough time so nothing's ever in a rush. So an example of this is a span that is between 2 established buildings in US East 1. And so you can see in January of 2022, the demand moved over to this almost immediately. We then added another span in the region, which reduced the demand on this span in about July of 2022. And then here, we had an operational event. And so this increased the demand on this span for a couple of days, at which point it came back. And then we had added more spans and more buildings through 2023. However, at this point, the capacity system decided to do something else. Rather than add a span somewhere else and reduce the demand here, we decided to scale this span. And so the green line shot up at this point in September to signify the increased capacity that we now had between these two buildings. And luckily for us, or maybe because the forecasting team are actually that good, the line of the forecast lined up exactly with the capacity requirement at that day. So we were able to, 6 or 9 months in advance, predict we would need this much capacity, and we scaled it. And so here we have our future forecast. We can see where we think it's going to grow in the future. And then I can also see from this planned effective capacity, there's enough wiggle room here for traffic engineering to bump that all the way up to the green line. So this span is good for many years, or months anyway to come, maybe years. So finally, in these design goals, we always want to come back to the features. What are the new things that we're enabling? So why are we doing this? And this may be because there's a new security requirement, we have a goal to reduce latency somewhere, or there's a new ASIC or new CPU that's being added. And so we always want to work our product design backwards from these. And so we hear from the service teams, they want to do particular things, and we want to take them into our design criteria to make sure we're building networks for the future. I can also tell you that anytime we do this and we hear about Graviton 4 or whatever else is coming in the Trainium line, it's never a case of we're just going to take this new component and swap it into the existing network. We're always going to use these chimes as an opportunity to do something more. So with that mental model set, I'll hand you off to Georgie, who can talk about some examples of building components to meet these goals.
Thank you. Oh, this one. Since we had introductions already, I'll get straight down to business. Today, I'll talk to you about how we progressively added software and smarts to our network and why we did it. We did it because we wanted to make it the best network for your workloads. We never wanted to make the best network protocols or the best network design, generically speaking. We wanted to make it the best for the users of a cloud provider. So the first design principle I'd like to talk about today is to lean on automation. You know, network operation centers, they look cool because they are inspired by NASA mission control. And anything relating to space tech, rockets, is much cooler than anything I do at work. But the thing about NOCs is that they are centered on humans. It's a bunch of smart people encircled by screens to try to make them better at identifying when something is wrong on the network and then reacting quickly to it. I tend to think that this is not what we humans are the best at. I tend to think that our forte instead is to exercise judgment. So in a way, NOCs, they try to make us better at doing something that we're not great to begin with. So how could we improve on that? Well, this operator here, unlike me, is never going to get bored and never going to lose focus. And that is true for any robots, including software that I write and deploy to AWS. And the advantage of that is that this software, because it's deployed to AWS, can scale horizontally. I don't need to build more screens, hire more people, build more rooms as my network grows. No, I just deploy that to more and more EC2 instances across the planet. So that was our journey in automation. We started with automating configuration deployment to devices, OS deployment to devices, then the collection of telemetry, that's data like SNMP data or NetFlow, and finally even more complex operations like traffic engineering. So if COVID has taught me anything, is that I'd rather be in a room like this one, encircled by humans, than in the previous one with screens around me. In this room, I have more opportunities to do the things that I'm good at, which is exercising judgment and comparing my ideas to those of other humans. And that's what we build. We build a network that out of 150 raw events every second that come out of those devices, only 2.5 are escalated to humans to take action on. And that happens because every single design of ours today considers automation from day one. That can be software, hardware, network interconnects. Everything considers automation from day one. The result of that is what this stat shows. A highly reliable network, despite it being built out of less than perfect components. That's very much like distributed systems. The next design principle is a mouthful, but hear me out. Despite our efforts in automation and in building the best devices we can, eventually things will fail. When they do, we want them to fail like this building in the picture failed. We want it to crash, release large amounts of energy, but not impact the neighborhood around it. Like the Tropicana Hotel next to us went down and we are still here, right? In AWS network, we want the same thing. We want failures to not create a last blast radius. We call it blast radius contention, to be very creative. At AWS, this happens naturally because of the availability zones. You know, the network is also built in the separate physically, geographically separate availability zones. So every time there's a failure, the design of the system itself constrains that failure to 1 AZ. But as we learn through history, and the Titanic is here to teach us, containing failures is easier said than done. And in some cases, even a good idea needs multiple iterations to get right, case in point. In our case, the frontier for improving on blast radius containment is beyond the availability zone, beyond the data center. Like a good example is the wide area network that connects data centers to one another, regions to one another, and then even regions to the internet. These parts of the network are inherently shared, right? The internet is not, they don't have 3 internets, one for every AZ, right? It's inherently shared. So how can we get that part of the network to also have some level of blast radius contention aligned to the AZs? I'll talk about that in a moment. The third principle I'd like to talk about today is about avoiding surprises. When you think about economies of scale, we might think that building bigger things is cheaper than building lots of small ones. But it's actually not true. Like, and it's easy to see in this airplane, like the Beluga. It's clearly to see that this one is much more expensive than a fleet of 737s, right? So how does that apply to network? Well, in network, we don't have airplanes, but we have these routers. The one on the left, a chassis router, can handle way more traffic than each one of the devices on the right, but it is also much more expensive than all of them on the right. But this story is not about cost. Cost is just one factor of it. The most important part is unprecedented scale. You see, as your business grows and you bring more workloads to AWS, and as more of you come to AWS, the more network we need to interconnect those EC2 instances to one another to allow the services to grow. And everything gets a little bit bigger day by day. Things getting a little bit bigger by themselves is not a huge problem. The problem is every complex system has sometimes they have like these hidden limits, like these cliffs that we don't realize are there, and eventually we cross over them and we have a failure. So we have these risks of unknown limits. How do we handle that? Well, in networking, we handle that by using the concept of fabrics. Fabrics are these network designs, routers and the topology between them, that we can stamp out, just like these car pieces are stamped out, the car panels, one after another to add capacity to the network. On the edge of the network, we can add capacity for internet transit or for content delivery network. Inside EC2, we can add capacity to incorporate more EC2 racks, to interconnect a new building, to connect buildings to one another, or to connect them to the edge network. The important part here is that inside each one of those fabrics, the scale is constant. The control plane of the network is handling an amount of scale that we are familiar with and we are certain it can handle because it has handled before. So if you've been paying attention to what I'm trying to put on the underlines here, this is all very much like distributed systems. The trajectory that I'm describing here is very similar to the trajectory that we as an industry follow when we moved from mainframes all the way to fleets of gravitons running in situ. Routers, if you think about it, they're nothing more than a server with a very fancy network card connected to it, right? And if you extrapolate from that one more step, we realize that the network and its control plane is basically the first distributed system we ever built as an industry. So let's see how that otherwise simple and obvious principle exists in practice. So the first thing I'd like to talk about is this talk Stephen had last year about intents. What are intents? Intents are these high-level concepts that exist in the same language that we think. So intents are things like amounts of traffic, waypoints on the network, direction of traffic, maybe a given destination like an ISP. And more importantly, what they are not things like IP addresses, BGP policies, communities, routing policies. They're not those low-level things. And an intent-driven network is a network in which there's a piece of software that translates between how I think, the intents, and how the network is configured. And why is that? Because that translation creates another opportunity for failure. Just like the automation story, this one also creates another opportunity for failures. So in practice, by deploying intent-driven systems to our network, for one example, we are able to improve the availability of EC2 instances to the internet in the last 3 years by 40 times. That means 40x less minutes that one EC2 instance somewhere was not able to reach the internet. So our journey into adding smarts has these 3 steps. First one is to automating monitoring, alarming, and even triangulating all that data to pinpoint exactly where failures are coming from. Next was to automate. Now that we know what is failing, how can I fix that failure? And the majority of the time, that is very simply just shifting away, sidelining the impacted device or impacted link. And having lots of smaller ones helps a lot here as compared to having big ones. And the final step is to take proactive control of the network, to start doing things like traffic engineering before we see a problem. Let's see how that happens in practice in 3 areas of the network. So the first one is outbound traffic engineering, is when traffic is going from EC2 towards the internet. Let me explain this diagram before I tell you what we did. On the very left, we have 2 availability zones. Then we have 2 edge sites, also known as transit centers. And I'm talking about a single internet service provider here, towards which we have 2 links on every one of the edge sites. Inside the links, you can see the link utilization, these black bars. So the first problem we wanted to tackle was congestion, right? When there's some kind of imbalance and you see the pink link, the second from the top, being congested. So our first crack of the problem was to, once that was identified, build robots that would mimic what we as humans did, which is identify which one of the links was congested, identify the top talker destinations, and peel them off with some more specific routes. That worked great, and that was our first step. Next, we started noticing that, well, if we balance the links out before there is congestion, if a spike of traffic comes, that second link from top to bottom, which is not congested now, we will not get congested in the first place. So that's what we did. We built a robot that would look for opportunities to balance traffic preemptively before congestion would set in, and that's the result. Then we started realizing that there's more to it than just congestion. There's also the fact that these 2 edge sites, they are not the same. Like in this example, the one on the top has a 10 millisecond path to the service provider, while the one on the bottom has 20 milliseconds. So within bounds, it would make sense to do something like that, to send more traffic to the one on the top than to the one on the bottom. So that's what we did. And at that point, we realized we had a full-blown controller, right, that would look at this, all these trade-offs, right? Like in this case, I'm a little bit less resilient to burst than in the case before, but within bounds, it makes more sense. So it would look at all these multiple dimensions of the problem and preemptively figure out the best path, the best waypoint for everyone, every destination on the internet. So, but I told you before that we want more than performance, right? We want the right experience when things fail. So how could we bring a level of AZ independence to this use case, to outbound traffic engineering? Well, the first crack at it was to start tunneling traffic from these AZs all the way to an edge site, a waypoint on the network. And why did we do that? Because we wanted to be able to deploy different configurations, different policies, one AZ at a time. So now, if I need to change the way traffic egresses, I deploy that to AZ1, and if there's a failure, my configuration had a bug in it, I can roll it back before I affect AZ2. But there is more. This is just the beginning. What we're working on now, and that's not released yet, is what this slide is showing, which is fully override the traditional network behavior, which would usually only be possible with something like policy-based routing. Ooh. Yeah. Network engineers love it, right? So fully override that behavior and try to place the traffic in a way that if there is a failure, chances are this failure is going to affect only one AZ and not another. So even in the static case, we are trying to optimize for keeping that promise of AZ independence, right? And I go back to how I started this, it's not that we're doing that because we are arrogant enough to think that we can do better than the entire industry has done throughout decades when coming up with protocols like OSPF and BGP. Like, that's not where we are starting that from. We are doing that because things like AZ independence were never in these protocols to begin with. So that's why we innovate and we get to the place where we get. It's all about your workloads. So the next use case is inbound traffic engineering. And that came later because, as you know, AWS is more outbound heavy. Most of our workloads are about serving data to the internet, not syncing data in from the internet. And because it came later, we could start it further ahead. We could start it from the controller point. And in this case, it's very interesting because unlike the outbound, we cannot fully control where traffic comes into us. Like the other network sending the traffic has the final decision. So you could only nudge it, like the cat is nudging the kitten there. So guess what we did since we could only nudge? Well, we built a nudging robot, right? And this robot, what it does is it plays this whack-a-mole game with the other networks we peer with in trying to push traffic away from paths that are getting congested or attract traffic towards paths that are more performant. And it does that all the time. And the result of that is that in our first iteration, we were able to bring down the time to mitigate inbound congestion from a little bit over 1 hour to a little bit less than 10 minutes, so a 7 times improvement. So the last topic I'd like to talk about today is traffic engineering on the wide area network. There are usually 2 approaches to this problem. Either you do it centrally or you do it in a distributed fashion. Let me start with the distributed way that this is done. This goes back all the way to the way telephone calls were made in the beginning of the previous century, right? You would stitch hop by hop a circuit towards the network, like literally by putting the pegs on the holes there and establish a circuit for people to talk to. That same theory, circuit switching, was reflected in protocols like frame relay, ATM, more recently RSVP. It has a couple problems that stem from its first come, first served nature. The first one is that it can converge to a less than perfect, a less than optimal solution. Second one is that it can find itself deadlocked. And it also has this concept of pre-clearance, right? This concept of admission control into it that doesn't really go well with AWS. Like no one of you would like to call an API before you actually make a request towards the internet or towards another region, right? It doesn't make sense. You just want to do it, right? So to fix the previous problems, as an industry, we built these pieces of software that have global awareness around the network and identify opportunities for optimization, and then go tell the nodes on the network to relinquish the circuits they have established before. Well, that brings us back to the central way of doing things, to build this global brain. And that's a great idea from an academic perspective, right? It's a puzzle. I know all the network demands, I know the network topology, and now I just have to figure out how to place that demand. This problem has two issues. The first one is like this. Imagine that I'm done with my talk here, the entire reInvent week, and I'm back at my desk in Seattle. And for the first time in my life, I write a software bug. I know it has never happened before, but there's a first for everything. Now, this bug gets shipped, and somehow it passes integration tests. Again, never happened before, but well, there's a first, right? And it gets deployed to the global brain of the network. What happens is a global impact, and that goes totally counter to the idea of blast radius containment that I was talking about before. So that's not something we'd love. The other problem is a little bit less severe than that, but is also bad, which is the fact that this problem is an O(n) squared problem. So as the network grows and I add nodes to the network, I increase the complexity of the problem in a squared fashion. You don't need a computer science degree to understand that this is very hard to cope with, so much so that the most recent research on this area includes using things like machine learning to solve the problem. Tick that bingo card again. So how can I have my cake and eat it too? Well, take something we hate, like tolls with dynamic pricing, into something we love, a high-performing network. This is how we did it. So imagine this hypothetical world in which every driver is very single-minded and has a single goal in life, which is to get to their destination at the lowest possible cost. The cost is the distance of the road that corresponds to the amount of gas or electricity they're going to have to use, plus the tolls on those roads. Now, because those tolls are dynamic, every time traffic increases in a single segment of road, like chances are that traffic is going to start moving to other parts of the road network. Well, you're starting to see how that can avoid congestion. But if your intuition is really good, you're going to start seeing that the next step, which is that the drivers that are going to start moving away from congested paths are the ones that have better alternatives rather than the ones that don't have better. These ones move first. If that was hard to see, let me build a more traditional example with a network here. I'm going to spend a couple minutes here to make sure we get it right because it might be a little bit complex. Every single link in this network here can carry 75 gigabits of traffic and is a 10 millisecond link. And I only want to have two traffic demands on this network. From A to B, I want to transfer 50 gigs. And from A to C, I want to transfer another 50 gigs. As you can see, the link in pink there, it's overwhelmed. I want to transfer 100 gigs, but it can only handle 75. But I have this path on the top that is a longer path, so it usually is not taken by traditional shortest path protocols. So with our traffic engineering solution, you're going to see on the graph on the bottom that the toll between link A and link B increases progressively from 0 to 10 milliseconds, which makes the path from A to C be the same 30 milliseconds either on the upper path, the scenic route, or on the shortest path on the bottom path. You can also see on the graph on the top how that splits the traffic between A and C, between the bottom path and the top path. You can see the green line going from 100 to 75, and the other lines there converging at 25 gigs each. So this is our final solution for the traffic engineering problem. We are not global blast radius here because each one of those controllers run independently on each one of those nodes. We don't have an n-squared problem because each one of those nodes only concerns itself with its surroundings, not with the entire network. But we still have some trade-offs, and one of them you can see on the screen right there. It's iterative. Some of those traditional network protocols I was talking about before, they can solve congestion or they can solve a problem in the network in a single cycle. This one takes a few more cycles to solve. In our case, I make those cycles really quick, and we make the algorithms that increase a little bit smarter than the ones you see on the screen. So that's what I had for you today. I hope you could get a taste for how we innovate on the network based on the idea of making the network better for your workloads.
Thanks, Georgie. So yeah, let's dig a little deeper at the lower levels and what we mean by ownership of the full stack and why I love these tiny plastic connectors. So as been mentioned before, the controllers and the services that we use to steer the network, they remove complexity from the physical layer. So we're able to elevate those problems up into software which can react better than the devices can on their own. And so normally this is where we could talk about the cool technology that we have, like the devices on the right. And we've said before, we don't like the chassis on the left. We don't like, decisions made by people who don't operate networks. We also don't like large software updates that maybe happen infrequently. And so there's elements of me that's a control freak, not always, but sometimes when it makes a difference, that's when it kicks in. And so here's an example of the racks that Georgie was talking about that we stamp out. We are very imaginative in our naming. This is called Amazon Rack 1. And it's very similar to the Outposts rack that you'll see if you go to the AWS Expo. These are the standardized building blocks. And this is the previous generation rack that we have. But you can see here, everything is to our specification. So all those devices are built to our spec designed by our people. The cables, the same thing, the power shelves, the battery backup modules, even the patch panels to the side. This rack is also not your standard 19-inch wide. We've gone a little bit wider. And so these are the bricks that we deploy as the standardized unit of capacity to build those fabrics, be that inside a data center or all the way out at an edge pop. But when we talk here at the conference about the software abstractions and the services that happen, all of that reliability and performance is great, but it is these tiny tangible details that give me the fizz. It's these tiny plastic connectors you can see circled here. Because inside a data center, we may have thousands of switches and hundreds of thousands of optics, but we can have 500,000 fiber cables in a single data center. And a lot of them go through intermediate patch panels like these. And so over the years, we have optimized how we build these buildings. So we start from the concrete pad, and we work all the way up in our process to passing customer bits. And what we realized is that we can speed up this process by pre-cabling. And so we've moved from these passive racks that you saw there before, beside the network rack and the compute rack, to these racks, or these patch racks up above. And what we're doing here is we're minimizing the space, and we're also iterating to trunk connectors. So we have 144 trunk fiber cables, the gray ones at the back that drop down, and then they go into this patch with these small form factor connectors that connect into this networking rack. And by moving to this model, we are able to remove 8 times the connectors in the data center. And so 8 times reduction in connectors, to me, is 8 times in reduction in things that can go wrong. And so that's a win because we're taking about 90% of the passive racks out of the data center, meaning there's more space for compute and storage to exist. It seems like a win-win, but there is a downside. At this stage of the build cycle, we don't have anything on the remote end. So I don't have protocols like LLDP to tell me that my circuit is connected correctly. So how do I detect miswirings? Well, we had a look at these things. And so these are dust caps. They go at the end of fiber cables. And in previous companies that I've worked for, they end up littered all across the floor in front of the racks. The reason they exist is to stop the dirt and dust getting in at the fiber connector and causing problems either at light signal or just consistency. And so we had an opportunity, like, can we do something better than these little pieces of plastic? And the answer, of course, is yes. And so we've worked with our vendors to create these loopback connectors. And so these come pre-installed in our compute racks. And what they do is they connect the circuit all the way from the router through the patch panels, all of the intermediate pieces, all the way to the end and back. And so we can identify where there are fiber miswirings, because humans have to plug them in at the end of the day. And so where there have been issues, we can identify them. This means we can resolve the issues before the compute racks show up and shorten the handoff time. So things like this, you'll see here, the orange one is the first generation, and it requires a human to go and splice a tiny piece of fiber in there. It gets glued in, and it becomes our connector. We've already iterated upon these with the gray ones you see on the left, which are solid state. And so there's little waveguides or mirrors in them that happen at injection molding time. And so not only are we reducing the time and labor required to produce these, but we're also able to produce many more of them than before. So it's these little tiny tangible things that actually give a pretty outsized benefit when we talk about doing this across the entire planet. So thank you for my little physical detour. The thing that I will point out that's useful here is with our ownership, we feel we can make changes at any one point along the stack and not have to affect everything. So we like that we can make small iterative changes to all of these things. And what's important is when we bring all these things together, they all feed back into the same telemetry system. So, of course, we have our passive telemetry system. We are sucking in as much information as possible from all the counters and sensors that exist in the network. And today, we're somewhere above 7 billion observations per minute. So that is a lot of traffic that's coming in. We also have our active monitoring system. This has been around for many years now. We started with our own instances running this, and we've since moved to running the package on the Nitro cards. And this is exercising all of the customer paths, even without a customer instance being on that host. And so this means, hopefully, we can detect the problems before you see them. And in general, we're north of 1.5 billion probes per minute on this system. But going back to what Georgie mentioned a few minutes ago, there's a problem with this in that as the density increases, so does the complexity of the graph. And so this is an ON squared problem. And as scale continues to increase and as the demands continue to increase, we want to do something a bit better. So we had a look and went, well, we own the routers, so let's just put the package on the router. So the great thing is we were able to take the same software package and deploy it on our devices. And we can now have these things we call device under test. And so we can do this at any point in the life cycle, be it on a device replacement, a first turn up, or just if we get an indication that maybe something's not great, we can exercise this segment without any of your traffic on it. So I can shift your traffic, put as much test traffic as I like, get confidence, and then put the device back in service. And so because we're doing this whenever we like, we can now reduce the requirements on our edge monitoring services. And so they can now go serve new challenges, new things that they were previously struggling to come up with the density that we have. And so now we can cover these dense meshes more easily. And so kind of put some numbers on the things that we're seeing. We're around about 25 billion alerts per year. That's 25 billion things that something's going wrong here. About more than 1 billion of them are actionable. And so a lot of them are going to get filtered out because it was a flapping link, we knew about it. We still wanted telemetry to know, is it flapping, but there's no traffic on it, so there's no harm. Out of those billion or so alerts, we come down to about 3 million distinct events. So we always want to have an event that's happened to get multiple sources. And so we kind of correlate that down to about 3 billion events. And the really cool thing for me, Georgie talking about the Network Operations Center, was that 98% of them never see a human. So the robot is taking it out of service, is finding the problem, is fixing the problem, and it never gets escalated to a human. About 2% of them do, and that's generally because we need some physical thing to happen, right? Something needs to get replaced or something needs to get interrogated a little bit more. But yeah, we're up at 98%, which I think is a cool number. So let's look at what's next. Some of the upcoming challenges and new ventures that are there. Well, like any infrastructure person, I'm always seeing things growing and expanding. And so I always need a little bit more space. So let's take my friend here. They have themselves a nice piece of land, a nice piece of quiet to get some work done. But let's think about what are their main concerns. Well, like everybody else, we need power and we need connectivity. So how are we going to do that in the future? What does that look like? Well, the regions that we have are continuing to grow at ridiculous rates. And so we're now looking at what things can we do that are beyond the traditional grow the region. And so we had a look at the technology that we built for local zones. And so this was about putting EC2 compute closer to the customer. Well, effectively what that meant was we were able to put EC2 compute further away from the rest of the region. And so what we're doing is we're using the same technology to put this compute closer to where the power lives. So you'll see here from these posts that are on aboutamazon.com, which was a great source for all of the links that I've put up. We've got order of $10 billion investments in places like Indiana and Mississippi. But if you look on that site, you'll also see things like the investment in wind farms in Mississippi. So the first wind farm in the state is going to be built purely to give power to our data centers, which we think is great. It's gone so far as to we are signing nuclear agreements for new locations that are coming up to continue this in an evolving way. And so, yes, we're using this technology now that we built for one purpose for other ones. Now, if I look at the opposite side in connectivity, when I was growing up obsessed with physics and spaceflight, I thought space was impossibly big. Right? By looking into space, it's like you're looking back in time. And that's because the speed of light was always there. But I never thought I would be in a day job where I was concerned that the speed of light was so slow here on Earth. To put that into context, in space, 300,000 kilometers per second is what we're looking at, or 9 quadrillion kilometers for this canonical light year that we think of. Sounds big, right? Well, why am I talking about this in a networking talk? Well, back on Earth, most communications is done across fiber optics. To be specific, the single-mode silica core glass fiber. That's a medium that's more dense than a vacuum, about 1.4x, which means we get about 2/3 the speed of light through our fibers. And so practically speaking, 1 meter is about 5 nanoseconds, and a kilometer is about 5 microseconds. Those numbers are meaningful with today's applications. So my practical example, I've got my 3 AZs in a region, and because we have set a latency target that happens inside the AZ, we work with our real estate folks to find new buildings to continue to grow these availability zones. Occasionally, they will come up and they will say, I have a great site, but it's just slightly outside the bounds. And how do I solve this? Like, I can't change the speed of light. Well, let's have a look. So about 25 years ago, the Defense Department and DARPA created this thing called hollow core photonic bandgap fiber. And this replaced the core of the fiber with a vacuum or even air. However, it kind of struggled to get out of the research phase, and they had a lot of difficulty adapting it to commercial use, which is why we don't talk about it today. But if I were to look at the benefits of this, for any given time period, my single-mode fiber will get me so far. If we had an Amazon hollow core fiber, we could get specifically 47% further than with single-mode fiber. And so we worked with a lot of people, and we have found some technology advancements. So for the optical nerds among you, you'll recognize this as an attenuation graph. This is the loss of light per kilometer for each of the wavelengths of light. And here with the photonic bandgap, you'll see there's really only 4 useful wavelengths of light, those troughs that exist. But also the loss is quite high. And so you can use this, but only in specific applications, and you've got to pump a lot of power to get through it. And so what we did was we worked with our multiple suppliers, and we came up with this hollow core fiber that has an attenuation graph that's much closer to single-mode fiber. You can even see the water peak there in the center, and that's where the water can get into the conduit, and water will absorb the light at a particular wavelength. And so generally, that's a wavelength we want to avoid. But what you can see here is this is a much lower loss than hollow core fiber, and it still has a high bandwidth. And so we're able to use this technology in place where we were previously using single-mode fiber. So if I bring this back to my practical example, for the same latency target using hollow core, we can now go further. This is almost a 50% increase, meaning we can add these new buildings which we previously couldn't, while still maintaining those targets that I talked about earlier. And the even better thing is this is cross-compatible with our existing fiber technology. So I don't have to go and replace all of our optical system. We can just replace the fiber parts in the middle. And so this is a really cool thing for us because we're now able to say to real estate, you can have an area that's over double what it was before purely by using this technology. So it's not often I can work with people and change a constant like the speed of light and meaningfully make something better. So that's pretty cool. It's also useful to talk about, these are only a handful of the physical innovations that we do at network scale. Like here's an example of the next generation of what you see on that fiber, on that up there. We have a handful of these at the expo, so please, if you're here at the show, come over to the AWS Village and we'll happily show them to you. I even have an example of the hollow core fiber as a preform. So this is a piece of glass that is before it's drawn out into the fiber that you know. It's a stick about this size. It's pretty cool. So if we kind of add the innovations we've had in the physical technology and the fiber space with the hollow core, we've even done things with multi-core fiber. And so this is able to, a couple of years ago we did it, where we were able to get 1728 fibers in a conduit that's normally used for 288. So we were able to massively increase it for areas in which we had a very small conduit and much larger demands. We have a multi-core fiber option too. Anyway, to kind of wrap up on this, it's been a pretty quick whistle-stop tour of the different things that we do. Hopefully you got an idea of the decisions and the internal products that we make and why this makes a difference at a planet scale. We're always going to be rooted in these design goals and continually seeking improvements, all the way down to these tiny plastic connectors. So thank you for coming. Georgie and I will be with some colleagues at the expo this week to take a look at the hardware. I do have one thing to ask you before you go. Inspiration for this talk came from feedback from last year's talk. So yes, please fill out the survey like everyone will ask you to do, but also please in the comments put down anything you would like to hear else that's in our space. So was there something here that you liked, or something here that we didn't talk about that you would like us to do? We're happy to do it again in the future. With that, thank you all very much for coming. Have a great day.